So in this lecture, we're going to talk about convex sets. And we'll start with some very basic definitions, like what's an affine set and what's a convex set. Then we're going to we'll look at a catalog of some very important examples, things like balls or half spaces or rays, things like that. Then we'll focus a bit on operations that preserve convexity. That's like the intersection of two sets or a sum, things like that. And then the basic idea is that'll form a calculus of convex sets. You can combine the basic ones with these operations and create quite a lot of interesting convex sets. We'll then move on to generalized inequalities, talk about what that means. That's an inequality, a vector inequality. And then we'll talk about some basic facts from convex analysis, separating and supporting hyperplanes, and the idea of dual cones and generalized inequalities. Okay, so we'll start with the idea of an affine set. So we have 2 points in Rn in a vector space, x1 and x2. And we form another point, we take a number theta, and we form the vector theta x1 plus 1 minus theta x2. Yeah, so it's a linear combination of x1 and x2, but it's a very specific linear combination. The two coefficients add up to 1. Okay? And geometrically, that looks like this. If I take theta equals 1, this gives you, of course, x1. If you set theta equals 0, you get x2. If you take theta equals a half, you're at the midpoint. That would be like right here. And as you vary theta, you move along this line. Now, when theta is negative, you're out here on the extension past x2 on the way in the same direction that goes from x1 to x2. And if you take theta bigger than 1, you're on this extension of the line over here. If theta is between 0 and 1, you're on the segment, line segment between x1 and x2. Okay, now we define an affine set to be a set where if you have any two distinct points in the set, then the line that passes through it is contained entirely in the set. So that's an affine set. And an example would be very obvious example is the solution set of a set of linear equations. So here, if you have 2 points, different points that solve a set of linear equations, so I have ax1 equals b. So if I have ax1 equals b, and I have ax2 equals b, then the claim is that the line passing through x1 and x2 is also in this set, which means satisfies this equality. And what that means is we'd have to look at ax, but that's a times theta x1 plus 1 minus theta x2. And the question is, what is that? And in particular, is it b? And it is, because this is theta ax1 plus 1 minus theta ax2. And that's theta b plus 1 minus theta b, and that is b, right? So that's the verification that the solution set of a set of linear equations is an affine set. Now, it turns out the converse is also true, that if you have any affine set, it can be written as the solution set of a set of linear equations. Okay, this brings us to convex set. So convex set, it's the same idea, except that we talk about the line segment. So the line segment between 2 points, these are two vectors in a vector space, that's any linear combination with the following requirements on the coefficients. The coefficients have to add up to 1, that's number 1, and number 2, they have to be bigger than or equal to 0. Another way to say that is they must have the form theta plus 1 minus theta, where theta is between 0 and 1, and so this is an honest mixture. Both of these two numbers is between 0 and 1, and they add up to 1. Okay? So that's the line segment. And a convex set, it's very simple. It's any set where it contains a line segment between any 2 points that are in the set. So if you have 2 points in the set, then the line segment between them must lie entirely in the set. Or another way to say it, very simple way, would be something like this, that if you have a point x1 and you have a point x2 in the set, there has to be a clear line of sight path between x1 and x2 within the set. So that's the idea. There's no hidden parts. Any point in the set can see any other point in the set. So an example of a convex set is this set here. And so here, if I take any 2 points, indeed the line segment between them fits entirely in the set. This set here, the Noguchi table set here, that's non-convex. And to show that it's non-convex, here's a point in the set, here's a point in the set, and the line segment between them is drawn right here. And you can see that it doesn't lie entirely in the set. Or another way to say it is that there's not a clear line of sight in the set from this point to this point. This set here, it's almost convex, but it's not convex. And it's not convex because, for example, here's a point in the set, here's a point in the set, and if I draw the segment between them, it crosses over that area where the boundary was not contained in the set, and so it doesn't contain the entire segment. So that's a non-convex set. Okay. Now, you have the idea of a convex combination. So a convex combination generalizes the idea that we just looked at of a line segment. It's basically this. It says I have k points now, where I used to have 2. And if I form a linear combination of the k points with coefficients theta 1 up to theta k, if theta 1 and theta up to theta k are just any real numbers, that's a linear combination. Okay? However, to make it a convex combination, these things have to add up to 1 and they have to be non-negative, right? So in the case when k is 2, it's exactly the same as the previous. It defines a line segment, right? So a convex combination is any element on a line segment between 2 points. Okay, so this is a convex combination. And you can think of it many ways. I like to think of the thetas as mixture coefficients, and you can think of x as a mixture. So it says take 10% of x1, 0% of x2, and so on, and up, and 12% of xk, and all these percentages have to add up to 1. Okay, that's the convex combination. People use the word mixture, but that's not a standard mathematical term, right? So people just use the term convex combination here. Now, the convex hull, and that's denoted conv of a set. That is the set of all convex combinations of points in a set, right? So if the original set were this finite set, these dark points, that's a finite set, then the convex hull of it is this shaded region here. And for example, if you take a point here, you can get that. Well, that might be a convex combination of 2 of them. Right? If I take a point in there, it might be a convex combination certainly of these 3, but probably of others. It's also a convex combination of this one and this one and this one, right? So there's no reason to believe that that convex combination is going to be unique. In general, it's not. It's just a point is in the convex hull if it is a convex combination of some points in the set. Now visually, you can think of the convex hull as simply something like the smallest convex hull that contains the original set. So, for example, our kidney or Noguchi table shape here, the convex hull is this shaded region. And so we have included all of the points in here, which previously were not in the original set, but they are in the convex hull. And now this shaded region is convex. So that's the idea of convex hull. Okay. Convex cone, that is simply, we start with the idea of a conic combination. And another name for that is a non-negative combination. So I take a linear combination of 2 points. That is theta 1 plus theta 2. Now, if theta 1 and theta 2 are general, it's just a linear combination. If they're non-negative and add up to 1, that is called a convex combination. And here the requirement for a conic combination is simply that theta 1 and theta 2 are non-negative. Right, so that's the definition of a conic combination. Some people do say that's a non-negative combination of x1 and x2. Okay? Now geometrically the picture is this. Here's x1 and here's x2 and here's 0. Then conic combinations is this sort of pie slice that goes between x1, x2, and 0. It sits in a plane. Even if x1 and x2 are in a high-dimensional space, this set of conic combinations lies in a plane that passes through 0, x1, x2. And then, for example, these points on this boundary, these are all the points that are multiples, non-negative multiples of x1. These are all the points that are non-negative multiples of x1, x2. Now, and all these points, for example, if I take something right smack in the middle, these are the points that are non-negative multiples of x1 plus x2. Another way to say that is that's everything of the form theta x1 plus theta x2. Okay, but generally it sweeps out this whole set like that. And a convex cone is this. It's a set that contains all conic combinations of any 2 points in the set, period. So if you have 2 points in the set, the entire all conic combinations are in the set. So that's a convex cone. What we're going to do now is look at some sets that we will see throughout the entire course, right? So these are sets like, solution sets of linear equalities and other things, and we're going to see these basically throughout the course. Right now, and in fact for the rest of this lecture, things are going to be a little bit dry because it's just the math. But I can assure you that we will use all of this later, and it'll make a lot more sense in a practical context. But for now, everything is just abstract, and that's just too bad. That's the way the course starts. So, okay. So let's look at hyperplanes and half spaces. A hyperplane is a solution set of a single linear equality constraint, right? A single linear equation, okay? And we'll take a not equal to 0, right? Because otherwise this thing is silly if a is 0. So that's a hyperplane, and it would be, for example, in R2, it's a line, right? The solution set of a single linear equation in 2 variables is just a line. In 3 variables, it's a plane, and in more variables, I guess that's why it's called a hyperplane, because it's like a plane, but it's in higher dimensions. So it's a hyperplane. And A is a normal to that hyperplane. So here, if this is, of course, this is just a line, but A is the normal to that. And this set, that's the set of all points that satisfy AX equals B. When you vary B, what happens is this thing moves up and down like that. These are parallel planes. That depends on B. So solution set of a single linear inequality is a hyperplane. A half space is this. It's the solution set of a single linear inequality. So here I say that A transpose X is less than or equal to B as opposed to being equal to B. If it's equal to B, it would be this line right here. This might be, well, B minus 0.1, and this would be B minus 0.2, and so on. So everything in this half space, these are all the points where A transpose X is less than the value B. And if you change B, you simply move the surface of this in a parallel way. You move it up and down. Okay? That's what this is. And now A is an outward normal to that set. Okay? So A is a normal vector. In this case, it's actually an outward normal. Now, these sets they're both affine and convex. And half spaces are not affine, but they are convex. I should say hyperplanes are affine and convex. Half spaces are convex. They're not affine. Now, this has to be shown. You can look at it and you can verify it visually and by intuition, but these are things you'd have to show. It's not particularly hard to show these things, but you have to. So let's take a look at, for example, a half space. The question we have to ask is this. If I take 2 points in a half space, the question is whether the segment is in it. And we'll just say, well, geometrically, it's obvious. And if you like, we could do this algebraically. To show this algebraically, we would say, suppose that A transpose X1 is less than B, less than or equal to B, and A transpose X2 is less than B. That means X1 and X2 are in the half space. And now let's take a convex combination, theta X1 plus 1 minus theta X2, and let's call that X. And the question then is whether A transpose X is less than B. And the hope is yes. And if that's true, then because X1 and X2 were arbitrary and theta was arbitrary between 0 and 1, I didn't say that actually, but I am now. If we verify this, then we'll have verified that a half space is a convex set. Well, A transpose X is nothing but A transpose theta X1 plus 1 minus theta X2. And sure enough, this is theta 1, A transpose X1 plus 1 minus theta A transpose X2. Now, that's non-negative, non-negative, so that's less than or equal to theta 1 B plus 1 minus theta times B. And I'm using the following fact here. This number is less than that number. That's our assumption. This number is less than that number. That's our assumption. And finally, we get this. and that's of course equal to b, and we're done. Okay, so I will never do a derivation this simple again in this course. This is just to show you the kind of argument you'd have to make that you draw a picture and your eyeball says, yes, that's convex, but these things actually have to get checked. Okay. The next thing we're going to look at are Euclidean balls and ellipsoids. So a Euclidean ball, Euclidean refers to the fact that we're going to use the 2 norm here, right? So the square root of the sum of the squares. A 2 norm Euclidean ball looks like this. It's the set of x for which the distance to xc, that's the center of the ball, is less than r. R is the radius of the ball. So that's what you mean by a ball. It looks like this, right? It's the solid thing here. There's xc, and the radius is r. That's a ball. Now this can also be written in a free parameter, or I should say a constrained parameter representation. All right, this is the style where you say it's the set of x for which a certain predicate evaluates to true. The predicate is this inequality. Here, it's a mixed thing. It says it's the set of all points of the form the center plus r times u, where u is a vector of norm less than or equal to 1. And you have to, of course, show that this is the case, but it's not hard. And this is convex, but again, I'm not going to show it, but it's true. A generalization is an ellipsoid. So an ellipsoid is the set of points that satisfy a quadratic inequality. Here's C as the center. And P is a symmetric positive definite matrix, right? So this is an ellipsoid. And here, for example, the semi-axes of the ellipsoid are given by the eigenvectors of P, and the semi-axis lengths are related. In fact, the square roots of the eigenvalues of P. These are the lengths of the semi-axes. And there is a corresponding, there's definitely a corresponding representation, just like this. Oh, I should mention the following. If you take P to be r squared, if I take P equals r squared I, then, in fact, this will give you, that's an ellipsoid, but it's also a Euclidean ball. So this is a generalization. The generalization of this representation for a ball is this one. It says it's the set of xc plus au, where norm u is less than 1. So you could even say something like this. It's the set of all things of the form xc plus a matrix A times u, where u is in the unit ball, right? So it's a linear transformation of the unit ball plus an offset, which is the center. Okay, so that's the that is a representation. By the way, this representation here is unique. In other words, if this is equal to another set with another P, those two matrices have to be equal. And I'm assuming that they're symmetric here, right? If they're not symmetric, that's false. But if they're symmetric, which you can assume without loss of generality, then it's true. Here, the A in this representation is not unique. There's multiple A's here that would give you the same set. In particular, if I take A and I multiply it on the right by Q, here, where Q is an orthogonal matrix, so Q is square and satisfies that, then for sure AQ can be substituted for A here and you get the same set. And the reason is actually quite simple. The reason is if I take something whose norm is less than 1 and I multiply it by an orthogonal vector, I get something whose norm is less than 1, and in fact it goes vice versa, so that's why it's the same thing. I'll just mention the following. We can make this representation unique here by insisting that A be symmetric and positive definite. So that makes it unique. And I'll let you figure out how that would be, how you'd make that argument. But the hint would be to take a singular value decomposition of A. Okay, the next in our tour of some of these very basic sets that are convex is the idea, we'll look at a more general norm. So if we have a norm, and a norm is nothing but a function, and it's usually written with, instead of as a normal function notation like this, it's usually written with its argument surrounded by double bars. That's the standard notation. The double bar, by the way, is supposed to make it look like an absolute value because a norm is something like, it's supposed to serve the purpose of an absolute value but in multiple dimensions. That's what a norm is supposed to be. Here are the requirements that for a function to be a norm. One is it always has to be non-negative. It's supposed to measure the length of a vector. So negative doesn't make any sense. And it should be 0 if and only if the vector is 0, right? So, and I think that's called definiteness. So these two together are called positive definiteness. It's a function that's 0 only if the argument is 0, and otherwise it's always non-negative. Okay, it has to be homogeneous of degree 1. That says if you scale x by a scale factor t, then that's the same as the norm of x times the absolute value of t. And that would work for negative. So for example, the norm of x is the norm of minus x. And finally, you have the so-called triangle inequality. And that says that the norm of x plus y is less than the norm of x plus the norm of y, right? So, and it's called the triangle inequality, roughly because, well, we'll get to it. But it says something like this, that if you have a point x here and you have a point y over here, then x plus y is over here, and it says that this distance here is less than this distance plus this distance, which is the same as this distance plus this distance. So at least for the Euclidean norm, where we all have a lot of intuition, this says basically that in a triangle, the longest side is certainly not longer than the sum of the lengths of the two shorter sides. Okay. Now the notation is when you write just a norm, it's a general unspecified norm, and usually what that means is the assertion you're going to make is true for any norm, right? Now when we're talking about a particular norm, usually there'll be a mnemonic or a symbol down below that tells you it's a particular norm. I mean, we've already seen 1, we've seen the 2 norm, that's the Euclidean norm, that's this, right? So we've seen that, but there's lots of others. Okay, now from a norm, this is supposed to be review. Now, from a norm, there's some very interesting sets you can come up with. One is a norm ball. That's the set of all points which have a distance as measured by the norm less than r from some center. And that's a norm ball with radius r. Here, norm cone. That's something much more interesting. We'll see a lot of this in the class as we move on. The norm cone is a set that sits in the graph space, right? So the graph space of something is the set of all pairs. That's in, say, Rn, and T is in R, right? So if you were to plot the graph of a function, that would be the set of all x and f of x, for example, right? Something like that, such that x is in Rn, right? That would be the graph of a function. It's a set of all things where x, you think of x as being down here, and then the height is what gives you f of x. Okay, so here, this is not the graph, it's actually what's called the epigraph of the norm, which we'll talk about later. But now it looks like that. And what it is the difference is it's an inequality here, and it says it's not just, so in fact in this picture here, this should all be filled in. That's a solid cone. It's a solid cone. I'm drawing the sort of the boundary, but in fact you should think of a solid cone that goes up like that. And people would call this a circular cone. That's if the norm is the Euclidean norm. That's a circular cone. Okay. And if you take a Euclidean norm cone, that's drawn here, that's called the second order cone, and we're going to be seeing a lot of it. Main assertion, norm balls and cones are convex. So by the way, the norm cone, as the name implies, is a convex cone. So by the way, you can't just say that. I mean, you know, technically somebody has to show these things. And well, that could be you on your homework or something like that. But that's something well, you can either trust us, read about it, or some of these things are very good exercise yourself. Just sit down and show that some of these things hold. By the way, some of these are trickier than you think. Showing something like this, the triangle inequality. It's not so bad for Euclidean, but for others, it's need not be that easy ahead of time, or if you haven't seen the proof in a while. Okay, this brings us to polyhedra. Another name for this is polytopes. I'll say a little bit about that in a minute. And that's defined as a solution set of finitely many linear inequalities and equalities. right? So if you have a set of linear equations and a set of linear inequalities, right? Oh, and here, this symbol means a component-wise inequality, right? So not everyone uses a different symbol, right? So a lot of people just write that this way because there's not that many different definitions of what it means for one vector to be less than another, right? So, but we'll write it with a squiggly thing. Okay, and that means that every entry of this vector is less than the corresponding entry of that vector, right? And of course, what that means is each row of ax less than or equal to b, each row defines a single hyperplane, and so it would look like this. Here's a1. Here's the boundary of it, and so the first row of this is all points kind of over here. Okay, it's that half space. That's all points that are over here, and the second row of this inequality that gives you all the points that are over here. And of course, if you take the intersection, what you end up with is this shaded set, something like that. Okay, so that's this is defined to be a polyhedron, and the plural is polyhedra, right? Another name for this is polytope. Is another name. And then what gets even more bizarre is some people distinguish between a polytope and a polyhedron by using one to refer to the bounded version. So if it's a bounded polyhedron, it's called a polytope. And then, believe it or not, you can find another author who exactly switches these, right? So that, for example, the general is a polytope and a bounded one is a polyhedron. So your best bet is just to stick with one and either put bounded or not in the front as a qualifier. So, okay. All right, so that's a polyhedron. Another set that we're going to see a whole lot is positive semi-definite cone. And the notation is this. Sn is going to be, that's the set of symmetric n by n matrices, right? So that's a vector space, right? Because it's closed under linear combinations and things like that. Oh, by the way, what's its dimension? It's like n plus 1 over 2. Yeah, because, well, I mean, you could just enumerate a basis or whatever, or you could just, very roughly speaking, you ask how many numbers do you need to describe a general element, and the answer is you describe the diagonal in the upper triangle and you're done, right? And so that's n plus 1 over 2 elements. Okay. If you put a plus at the bottom, that's the set of positive semi-definite n by n matrices, and that's the set of that. What that means, of course, is that this is the following. This quadratic form. It says that z transpose xz is bigger than or equal to 0 for any z you pick, right? So that's what that means, and that's a convex cone. And what that means is, if you take two positive semi-definite matrices, if you take a non-negative linear combination of them, you get another positive semi-definite matrices, right? So see, these are covariances, if you like to think statistically or something like that. They're covariance matrices. If you put plus plus, it's something like positive, and that's the set of positive definite ones, right? So these are, I guess, covariances of random variables that are non-degenerate, or I think there's some name for it. But basically what it means is the covariance matrix is positive definite. Okay? And here's an example. Here is the positive semi-definite cone. Here is S plus 2. And it's got a dimension 3, right? Described by x, y, and z. And here it is plotted. I mean, you can't see it. Actually, this should look kind of, I've had people describe all sorts of things, like it's the front of a ship or something like that. I don't know. But what it really is? It's the same as that cone. It's the same as an Orn cone. It's just rotated. That's not hard to show. I mean, you just write out what it means for a 2x2 matrix to be positive semi-definite. That's what it means. Determinant's positive. But I won't do that, but I'm just saying that's what this is. Okay. So, one of the things that you're going to need to do as a practical matter is this. I mean, we'll talk about convex functions, like maybe definitely next week. But one of the things you're going to have to do is be able to determine whether a set is convex or not. That's going to be one of the things you will absolutely need to know. And there's not that many ways you can do this, but the basic one is this. And this is sort of, when you're starting off or something like this, and sometimes it's the right thing to do, but actually quite rather rarely. It's this, is basically you go right back to the basic definition. And it says, to show that a set is convex, here's what you do. You say, give me one element, give me another one, they're arbitrary, give me a number theta between 0 and 1, and then verify that the convex combination theta x1 plus 1 minus theta x2 is in the set. That's your, you can always fall back on that. But more interesting, and something that's going to fit with a lot of other things in the course and other stuff that we're going to do, is actually to come up with an interesting, is actually to use a calculus of convex sets. That's actually a more interesting, it's constructive. It's also going to fit in with sort of a more modern computer science-y type view of all this. And if you actually wanted to do any of these things, this is going to be much more useful. Oh, and I might add, you will be doing these things, so it will be useful for you. So the idea there is you have a calculus. You have a bunch of atoms, right? You have basic sets that you know are convex. We've already seen some half spaces, solutions of linear equalities, polyhedra, things like that. Norm balls, norm cones, positive semi-definite matrices, things like this. These are atoms that are convex. And by the way, somebody has to show at some point these verify their properties, right? You do that. And then the key is this. You use operations that preserve convexity. And then you build up, you generate new convex sets from your atoms and these operations, right? And in fact, if you like to think this way, it's a very good way to think. It says that what it means is that we'll be messing around with sets that are described generally by expression trees. There'll be an expression tree. There'll be your set, and you'll go down the expression tree. The leaves will be atoms. There'll be things known. That can change too, right? I mean, but it'll basically, these will be things known to be convex. And then at every node in the tree, there'll be some operation that preserves convexity. Everybody following this? So, or if you like to think of it, I mean, it's like a calculus. Okay. And we'll look at some of these. We'll look at some of these things. Some of these are kind of obvious. Some are not, and we are going to hit some ones that are not obvious today. So at least then you can say in the first lecture, it is not true that you didn't hear anything. It's not true that you didn't learn anything. Okay. All right. So the first one is intersection, right? So intersection of any number, finite number, infinite number, uncountable number of convex sets is convex. Right? And by the way, these things need to be shown. That's a two-liner or something like that. I'm not going to do it. I would recommend that you sit down and show some of these. So let's look at an example. Here it is. S is going to be the set of vectors in Rm for which this polynomial P of t, which is going to depend on x, we'll get that in a second. This polynomial P of t is less than 1 for t, absolute value less than pi over 3. Now P is this. It's this. It is it's so-called trigonometric polynomial, partial Fourier series, whatever you want to call it. Okay, so there it is. That's what this is, right? Some periodic function with, I guess, up to n plus 1 Fourier coefficients or something like that, right? There it is. So that's it. In other words, I'm going to identify with each vector in Rm, well, a trigonometric polynomial, right? That's it. Oh, I didn't put constants in here, but who cares? Okay, so that's it. And what this says is it is the set of all points in coefficient space, because that's really what Rm is now. It's the point of coefficient space where the corresponding polynomial, if you plotted it here, that between, 0 and pi over 3, it's between minus 1 and 1. That's the picture. Everybody got it? Okay, now, you might ask a question like this. You might want to, actually because of your training, you might want to, right? If you have this 19th century mathematics training, otherwise known as the training we now give all our students. But if you are trained in that, you will have this urge to look at this and try to write out some secret form. Let's work out what is S. Let's write down some formulas for S, right? Let's try to figure it out. Okay, well, and you could do that for m equals 1, 2, 3. By the way, about m equals 5, it's impossible. There's no formula for it, right? That comes from Gauss's theorem about polynomials and things like that. So, there's basically there is no formula for this. For m equals 10, there's no formula for it. There's no way to write down this is true if and only if x satisfies the following things, right? Okay, so that's not quite true. I misspoke there, but it doesn't matter. Anyway, it's fantastically complicated. Okay, so all right. So first let's check if it's convex. And the first thing is to just make sure that on an intuitive level we all agree. So what we're saying in convexity is something like this. What we're saying is that if you have 2 points, let's call it x and y. These correspond to polynomials, let's say p and q. And so what we're saying, and by the way, you don't have to check for theta, all thetas between 0 and 1. It's good enough to show it for theta equals a half. That's, if you can show it for theta equals a half, you got it, right? So that's with a, I mean, you don't need much more about a set to say the following. A set is convex if and only if it's closed under averaging 2 points, nothing more, okay? And you do need a little bit more, but that's getting into weird analysis, okay? So, but let's see what that's saying. It's saying that if I have 2 polynomials, here's one, right? And here's another one. Let's see, here's another one. And they're both in that set because on the region 0, pi over 3, your value is between, plus and minus 1. And now we form the average of the coefficients. But when we form the average of the coefficients, you're actually forming the average of the polynomial. And the average of the polynomial, indeed, is between minus 1 and 1 on that little interval. And so it's in the set. Everybody got that? That says this set S is convex. And when m equals 10 or something like that, it means we don't have a very good way to describe S. There's not an explicit way to say this is what it means to be an S. I mean, there is one, but we'll see it later in the class, right? It's really complicated, right? So the idea is it can be easy to verify convexity even if you don't have a simple description of the set. That's actually a very important thing to know, right? Because in fact, that's going to be fantastically useful, this idea. Okay, so here's a super quick proof of it. It's really simple. It goes like this. What I do is I'm going to introduce S sub t, and that's going to be the set of x in Rm for which P of t is less than 1. Okay? So that's St. Okay? And notice it's just a single point. And I want you to tell me, so that's for each t, I get this set. I want you to tell me what is that set, what does it look like? It's the intersection of 2 half spaces, right? Because this P of t is a linear function of x's, right? It's actually just the inner product of, cosine 2t, that vector with x. So it's a linear function. That says a linear function lies between 1 and minus 1. A linear function less than 1, that's a half space. A linear function bigger than minus 1, that's a half space, actually oriented the other way. And what it says is that is a slab. That is the correct term for that. It's a slab. It's the intersection of 2 parallel half spaces with opposite orientation. Okay? That's a slab. And what that says is I can write S this way. S is the intersection over an uncountable number. But you don't have to get bent out of shape over that. It's this. Right? So it's that. It's the intersection of those slabs. And here is the picture. So here's S, and you can see it's got some curvature if you look in there. And what these lines show is for some values of t, maybe 20 values of t or 10 or something like that, what we've done is we've actually just plotted the 2 slides. Now, when the slab, when t ranges between 0 and pi over 3, that slab, it rotates and its width changes, right? And it says if you take the intersection over all of those slabs, the inside is what's left, that gives you the set S. Okay? So that's, all right, so that's the idea. Okay. We'll look at a couple more of these operations. Affine function. So an affine function is linear plus an offset, right? And by the way, some people call this linear, but I hope only in informal context. If you're with people you know very well and stuff like that, you can do this, right? But it is not linear. It's affine. Okay. So it turns out that affine mappings, they preserve convexity in both directions, forward mapping and reverse. And here, again, this is standard mathematical notation, but it's something we should go over. If I have a function, then I can overload that function to take as argument a set. And what it means here is the following. it says so here, f of s is the set of all things of the form f of x where x is in S, right? So that's absolutely universal standard notation to overload a function so I could talk about a function and I could say I could ask about what is the function of, say, a unit ball or a polyhedron, and the answer is it's some set. It's all the values or something, right? Now the inverse image is also absolutely standard notation, and it is not maybe what you think. Okay? So there's two ways to parse that, and I'll explain what they are, or to interpret it. So one way is to simply take the inverse function, f inverse, and say that it's something of this form. So you take the inverse function, and then it's the same as that. But in fact, the inverse image of a set under a function is defined even when that function is not one-to-one. By the way, those are the cases that function does not have an inverse. So this is defined, f inverse of c is defined for a set, even in cases when f is not invertible. So f inverse the function does not even exist. F inverse the relation does. Okay? So, and it's simply defined this way. It is the set of points that map into the set, right? So if that's your set C, then you just simply apply F, and if you land in the set, in fact, let me have them land at the same point. There you go. Then these 2 points are in F inverse of C. And notice that they both have the same value of F, and therefore F is obviously not invertible, right? But this notation does work. Oh, and by the way, when the 2 contexts agree, they are consistent, right? That's required of notation, right? That if you have ambiguous notation, it must be the case that when 2 contexts overlap, that you assign the same semantics, right? And that's correct here. Okay, so affine functions preserve convexity both forward and reverse. So images and inverse images. Okay, and that's and again, you have to show this, but let's look at some examples. Well, some are obvious, right? If you scale a set, if I multiply it by 2 or 3 or -5, that's going to preserve convexity. If I translate it, if I move it here, that's going to do. I mean, another one, of course, is if I rotate it and stuff like that. If I project it, if I take a set which is in R10, and I simply look at the first 5 components of it, right? So, well, let's do an R3. I take a 3-dimensional object, and I only look at x1, x2, which is basically the same as making its shadow on that plane. Then that's going to be convex. That's kind of obvious, right? That the shadow cast by a convex set in R3 is convex. It's a convex set in R2. Okay. Here's one. This is something we'll see, fairly often. It's called a linear matrix inequality. And so it says this. I have a bunch of matrices, A1 through AM. I form the sum of xi times AI, right? And I say that's less than or equal to B, where B is a matrix, a symmetric matrix. This is in the matrix sense, right? And the idea is this is supposed to look like a linear inequality, right? Written out, right? Well, an ordinary, if the A's were lowercase, B was a number, and that squiggly was an ordinary inequality. Oh, by the way, if the 2 notations would match up then and it'd be the same thing, then that would be a half space. But here it's defined by matrix inequalities. That's called a linear matrix inequality. It's convex. And the way you know this is convex is the following. I'm going to form a function, which is f. It's going to map Rm into Sp. And it's going to be this. It's going to be B minus sum xi ai. Okay? So that's my function. It's affine. That's an affine function. And its inverse image, the inverse image of that function of the positive semi-definite cone is this set, this linear matrix inequality, right? Because what I'm saying is the set of x's for which this thing here is positive semi-definite, that's exactly this set here. I mean, you'd have to put something on the other side, but it's the same thing, right? And so that tells you that that's it. You'd have things like this. The hyperbolic cone. That's the set of points where x transpose px, that's a quadratic form, is less than some c transpose x squared, and c transpose x is bigger than or equal to 0. That's actually convex because it's the inverse image of the standard cone, norm cone, two norm cone under an affine mapping. And I won't go into that, but I'll let you look at that. Okay. Now we're going to get to something that's actually different because so far everything so far is kind of obvious and two lines and stuff like that to show everything. Now we're going to go up to something that takes 4. So here it is. The perspective function is a function that maps, well, let's say Rn plus 1. I mean, it could also map Rn into Rn minus 1. But let's say it maps Rn plus 1 into Rn. And it's this. It's the perspective function is p of x and t. You simply divide the first n elements of the vector by its last component. That's called the perspective function. But it's also called projective, I think, in some areas, right? It's called projective mapping. Okay. And the domain is the half space where t is positive. Okay, so that's what it is. And it's the effect of sort of normalizing by the last component or something like that. By the way, it comes up a whole lot more than you think. So, okay. So it turns out inverse images, forward and reverse and inverse images of convex sets under the perspective mapping are convex. And that is not obvious at all. Okay, it's true. It's not hard to show. Like I said, instead of 2 lines, it's 4. Okay, but it's not obvious, right? So it says that if you have a if you have an operation that does this, it says if I have a bunch of points in a convex set, and then I simply take the first chunk of the vector, divide it by the last element, that gives me a new set in one smaller dimension. That's convex. Okay, and it's not obvious. I don't think. Okay, so. And a generalization, it's not even a generalization of it. If you precompose the perspective function with an affine function, you get something called a linear fractional function. And that looks like this. It's a function that's an affine divided by affine, and the denominator is scalar. And the domain is where the scalar is positive, right? The denominator is positive. So that's called a linear fractional function. And probably if you've taken a course on vision, for example, you would have seen these and maybe some other things as well. It comes up in other areas as well. It's very basic in probability. This is called conditioning, right? If you work out what you do when you compute a conditional distribution, that's what you're doing. You're taking an affine function in the numerator, and then the denominator, you're normalizing. You're normalizing sort of by the probability of that set. That's exactly this. So conditional conditioning is also a linear like a linear fractional function. Okay, and this preserves convexity. Okay, so a quick example is something like this. Here's one. Here's a mapping from R2 to R2, and the domain is x1 plus x2 plus 1 is positive. That's the domain of F. Okay, and so the domain is everything over here. That dashed line says, that's out of the domain. Right? So is the line. It's not in the domain either. And the image, it says that the image of a convex set under this mapping is convex, right? So, by the way, it's kind of boring for me to show that. For example, if I showed a circle here, it would be like an ellipsoid over here. So it's kind of boring to show. But just to give you a rough idea of what it does, here's a non-convex set, and here's its image. And if you look at it carefully, you'll realize something about it looks very natural. And then you'll understand, and it says that it tells you why we are all intimately familiar with perspective and linear fractional mappings. This is actually what this looks like on your retina. Here's why. Let's take this set here, and let's fly above it. Let's put it in 3D. So it's lying down, and you have that shape, whatever it is, C. And let's fly above it like this. And let's get maybe like right here, or actually we would be like right here. Let's be there, but let's go a couple hundred meters in the air, and let's look down at it. And what would you see? You would actually see exactly that, right? And this is foreshortening, right? Because these correspond to like these things, the things that are close to you, right? And so they're stretched out, and the stuff that's in the distance is shrunk, and that's this, right? And that would actually be sort of the horizon. That's that thing. That's looking way off. That's if you look parallel, you look way out to the horizon. Okay? So in fact, And if you've had a class on vision or something like that, um, you would you would know this, that actually what we see all the time, I mean the image on your retina is a linear fractional mapping, or for that matter the image on a camera plane is a linear fractional mapping of, well, neglecting little optical aberrations, is supposed to be a linear fractional mapping of the 3D object space. Okay? And so what this says is the following, and it's kind of cool. It says this. It says that if an object is convex in 3D, then it says that the image it puts onto your camera or your retina is convex. We're going to look at one more topic, and that's generalized inequalities. So this is going to be very useful for us. The idea is you generalize inequality on R to other contexts, and you've all undoubtedly seen this, for example, in the context of a matrix inequality. So here it is. If you have a convex cone in Rn, it's called proper if it satisfies a couple of things. First of all, it's closed. In other words, I'll draw one in R2. It says it's got to contain it has to contain its boundary elements. Okay, so it's closed. The other thing is it's solid. So it has to have non-empty interior, right? So for example, that's a cone. A ray is a cone, right? So a ray is just a point that goes from 0, goes off in some direction. That's a ray, and it's a cone. But it is not solid, right? I really like these terms, right? Because they are very evocative of what it means. So solid means it's not flat or something like that. It means there's a ball in it. Okay, and it's pointed. Pointed says it doesn't contain a line, right? So for example, a line is a cone, right? A line is a cone, but there's something, I mean, technically it's a cone, and that's just fine. It's a cone. But there's something about it, because the whole idea of cone for us is supposed to mean, or it's supposed to evoke the idea of something that's asymmetric, that it goes one way, but not the other, right? So, I mean, well, that is a cone. What it is not a proper cone, because it's not pointed. So pointed means that it doesn't contain any line. It says that in any ray, you can't have a ray and it's negative both in the cone. That's what it says. Okay, that's what pointed means. Okay, so here's some examples. Non-negative orthant, right? It's denoted R plus to the n. You know, it's this set in R2. Positive semi-definite cone, that's pointed. Sorry, that's proper. Of course, it's pointed. Non-negative polynomials. So there you go. The set of coefficients of polynomials that are non-negative on some interval. That's a proper cone. Okay? It's a bit of an obscure one, but it is one. Okay? So these are proper cones. Now, when you have a proper cone, you can make up an inequality out of it. And the way you do that is really simple. You simply say that x less than or equal to y with respect to the cone k. That's how you read this in English, right? And it's denoted x squiggly less than or equal to y sub k is with respect to k. And that simply means y minus x is in the cone, right? So, because the idea of the cone is supposed to define what you're going to call your non-negative elements. So what we do is, armed with this idea of a cone, and the cone is going to be, roughly speaking, our non-negative elements. Oh, by the way, here's a really simple cone. Ready? The set of non-negative numbers. Okay? And that's a proper cone. I mean, it's kind of silly to take an elementary idea and make it so complicated, right? Kind of pedantic. But anyway, that's what these are supposed to be. And so then you can define an inequality. An inequality is defined in the obvious way. It says that one thing is less than another, says that the difference is non-negative. And strict inequality means you're in the interior of the cone, right? And so for example, if I take the cone as r plus to the n, then this inequality here means simply that you have component-wise inequality. It means that each element, I mean, technically what it means is that y minus x is in the non-negative orthant. Non-negative orthant is all vectors with all entries non-negative. So that means this, right? So, okay. Matrix inequality. You've already seen this, presumably, somewhere. It says this. It says that one matrix is less than another. You'd say x is less than or equal to y with respect to the positive semi-definite cone. That would be the formal reading of this. And that means simply that the difference is positive semi-definite. But you've seen this before. You've seen matrix inequality. Now, these two are so common that we drop the subscript. So if you see two vectors and somebody writes that, or if these are two matrices and they write that, I should emphasize the curvature a little bit more, like that, right? The default is that the default subscript that you will fill in is r plus to the n and sn plus here, okay? Meaning, so if you see x squiggly y and they're vectors, it means element-wise, and if they're matrices, it means with respect, if they're symmetric matrices, it means with respect to positive semi-definite cone. Okay, so these are kind of standard. Now, when you introduce some notation like this, obviously the point of introducing notation like that is it's supposed to evoke, that it's supposed to be like ordinary inequality, but ordinary inequality is defined only for numbers, right? So when you generalize notation or something like that or overload it, the idea is it's supposed to suggest things that are true for the original, the non-generalized one. It's supposed to suggest things that are true in the generalized setting. Okay. By the way, not everything it suggests will be true, so you're going to have to be very careful. So, for example, how about this? It says that if x is less than or equal to y with respect to a cone and u is less than v, then x plus u is less than or equal to y plus u. By the way, you have to check this. I mean, I'm not, I'm allowed to just say this, but then you should take random ones of these and check that it's true, right? So that kind of makes sense, right? If one number is less than another number is less than another, then the sum of these two is less than the sum of those two. I mean, okay, fine, right? So that's true. Okay, I'll tell you there's some things that are not true. Here's one. Here's something true for numbers. For any two numbers x and y, either x is less than or equal to y, or y is less than or equal to x. That's true for numbers. And by the way, that's got a name for an ordering, a partial ordering. That's called a total ordering or a linear ordering. So if you've seen this in some class somewhere, great. So that's what it means. But in general, you don't have that. In fact, that's what it means, I guess, in general, to be a partial ordering. So we can actually have cases where one vector is not less than another, in which case, well, I'll say something in a minute, and the other vector is not less than the other one, in which case we say that x and y are incomparable. That's one name for it, right? And you don't have that on R with ordinary inequality, right? You can't say, 12.6 and minus 2.3 and say, no, sorry, they're incomparable. Neither is bigger than the other. I mean, it's silly, right? But this already happens. I mean, obviously it happens for vectors immediately. In fact, somebody give me a pair of incomparable vectors with respect to the ordering generated by, say, r plus 2. Thank you. So there you go. 2, 1, and 1, 2. And this is false, right? And this is false, right? And so they're just incomparable. Okay. And what happens then is this, and you're going to have to get used to this. It's actually going to play a big role in the course, and it's a very basic thing, so you have to think through all this. It's actually quite interesting. It's this. What happens when you go from a linear ordering or a total ordering to a partial ordering is the following. By the way, a lot of things you think are still true. But the one thing that happens is really interesting is your idea of minimum or smallest or something like that. It splits into two different concepts. That's what happens. And so they're called minimum and minimal, and it just says it's a much more complicated idea. And let's see why. I mean, there's actually other things in between, but let's look at them. And by the way, we're not doing this for the math. You'll see later that this has all sorts of real implications. So a minimum element, you say if you have a set S, then a minimum element is defined to be this. It is a point in the set like this. You'd say that X is the minimum element if it is comparable to every other element in the set and it's smaller than or equal to it. That's what it means to be the minimum element. And yes, it's unique. That's easy to show, actually, because you know, if x, you have x less than x and the other way around. So, okay. Um, okay, so that's the idea of a minimum. A minimal element is going to be this. It says that a point in a set is a minimal element if the following holds. It says that if you're in the set and you're less than or equal to that point, then you're equal to the point. Right? Now you can rewrite, there's other definitions of minimal, you can rewrite it and stuff like that. And right now this is utterly context free, so it means nothing. But later you'll actually realize this is actually quite useful and quite important, right? This idea. And just to start getting the idea in your mind now for what the difference is geometrically, it's this. Let's look at an example. The cone is with respect to r plus 2. And so what that means is we have points here. And what it says is if that's, for example, x, these are all the points that are bigger than or equal to x, right? And these are all the points that are less than or equal to x in this cone. And what are these points here? Incomparable, right? So these are all the points, these are the points that are incomparable with x, right? It is neither true that x is less than or equal to them or that they are less than or equal to x, okay? So minimal says the following. It says that if you are in S, then you must be comparable to it and bigger than or equal to it. And that says that the set S has to lie sort of like that, right? It says it's over here, and it's in the, and that's the point X, right? So that's this picture. So here X1 is, and it's unique. It is the unique minimum of S1. Okay, and that's kind of the natural generalization of minimum, which makes perfect sense, right? It's going to turn out one that's actually much more useful is actually this, is minimal. Minimal is this. Here's a set S. It has no minimum point. There is no minimum there. There's no point in that set that is comparable to every other point in the set and less than or equal to it. One doesn't exist. But what there are minimal points. And a minimal point is this. It says that if you're here, it says that if you're in the set and you're comparable to it, right, then you cannot be less than x without being x. That came out really long and weird, but you got the idea, right? So what that says is the following. It says if you draw the set of points down here, which are the points comparable to x and less than or equal to x, it says that the intersection of this set and S2, the only possible point is x2. That's what it says. Okay? And so that says that every point on this face here is minimal. Okay? How about any other point? I mean, there's no other point that's minimal, right? Because to check if a point is minimal, you take the point and you draw this set that goes left and down, and you intersect that with the set. And if you get anything other than a singleton, which is the corner, then it's not minimal. So separating hyperplane theorem, it's quite straightforward. Geometrically, it's extremely intuitive. It says the following. If you have two convex sets, say like D and C, and they're disjoint, then it says that you can actually put a hyperplane in between them. Okay, so that's a statement. And or another way to say it is, or if you have taken a course on machine learning or something like that, you can say that there's a linear classifier that will distinguish C and D. Again, this is if you've taken a machine learning course. And what it says is there is an affine function, or a linear function, if you like, A transpose X. And that linear function is less than or equal to B here, and it is more than or equal to B on D. So there's a sort of a linear classifier. By the way, we'll talk about these things later in the course. But this is the idea. And I think last time it's kind of clear how this would fail if C and D were not convex, right? That you would have disjoint, non-convex sets that cannot be separated by hyperplane. Okay, and there are many variations on this. Variations that talk about strict separability. Strict separability is you replace these inequalities with strict inequalities. And these require additional conditions and so on. And this brings us to the supporting hyperplane theorem. And this says the following. First of all, a supporting hyperplane, this is something we'll see a bunch of times. But the basic idea is you have a set, and then you have a hyperplane that touches it at a point. and has it touches it, doesn't go into it, right? So that's called supporting it. I guess the idea is it's like a contact point, and if you're oriented the right way, it could actually provide a force that would hold it or something against another force like gravity. So that's a supporting hyperplane. This is a picture of what a supporting hyperplane looks like, right? So here you would say that this hyperplane supports C at x0. So that's the idea. Another way to say it is there is a linear inequality, or it's a half space, which does not intersect, or many ways to say it. It's a point on the boundary of C, and there's a half space that contains C. That's one way to say it. Okay, so that's a supporting hyperplane. So that's the idea. And this is easy to, you could say the following. If a set is convex, then there exists a supporting hyperplane. And actually that's easy to show. You go back to the separating hyperplane theorem and you apply it to two things. If you have a point x0, which is in the boundary of the set C, then you simply apply it to, and C is convex, you apply it, the separating hyperplane theorem, to the following two sets, x0 and the interior of C. Okay, so you take, these are both convex sets. They are disjoint. Well, that's just one point. X0 is not in here because it's in the boundary, and then you apply the separating hyperplane theorem. One thing we want to talk about, this will come up a lot more in the future. Right now, it probably makes very little sense, but we might as well just get the definition out there. And you'll see it's going to play a very big role later in the course. And it's the idea of a dual cone. So if I have a cone, K, and you can imagine a cone as looking something like that, right? That's a cone. That's the point 0 here. That's a cone. And the dual cone then is the set of vectors that make a non-negative inner product with every element of this cone. Okay, so that's the idea. And so to evaluate if a point is in the dual cone, well, let's just check. So here, if I ask, is this point y in the dual cone, if this is k, then what we do is we look at the following. This half space here, that's the set of points that make a non-negative inner product with y, right? It's this half space here. Okay? And you can see that, in fact, every element of k is in it. That says that this point y is definitely in k star. Okay? That's in k star. Now, a point like this here, let's call that y tilde, that's not in k star. And the reason is, well, it's quite emphatically not in k star, right? Because, in fact, there are tons of points in k that make an inner product with y tilde. Okay, so that's the picture. So if you wanted to draw, for example, the dual cone of something that looked like this, if this is k, what you'd do is you'd go out. This point is right on the boundary, right? Because here, if you look at the non-negative, the points that have a non-negative inner product with y, if this is y, it's this half space, and you can see that's just barely touching k. If I were to push this just a few degrees to the left, it would be outside k star. So that's the boundary of k star. That's one. And then the other is this. I'd go out that way, where it's just about to pull out of there. So this here, this thing would be k star. Okay? This example already suggests some interesting things, which is generally true of like dual relationships. So here what you can see is kind of something like this. If k is kind of thin and sharp, then k star is thick and blunt. And you can kind of see that's the picture here. This also suggests, by the way, that k star star is k, right? And in fact, whenever someone says dual or conjugate, or I mean, there's several words in mathematics that kind of give you the hint that if you do it twice, you end up back where you started, right? Transpose, adjoint, dual, conjugate, all these kinds of things. Now, of course, it's not always true, right? There might be conditions, but these are the things that are hinted by actually just that language, right? So, and we'll see a lot more about this later. So here's some examples. Let's take the non-negative orthant. There, it turns out the dual cone is exactly the non-negative orthant. So what it says, that's called self-dual. It means that its dual is itself. Oh, and by the way, in terms of angle and bluntness and sharpness, it basically says that a 90-degree, something like a cone that's 90 degrees is actually self-dual, right? Because it's actually, that 90-degree cone is right on the boundary between blunt and sharp, right? So this kind of makes sense. This also turns out, I mean, someone has to show this, but what this basically says is the following. It says that a vector is non-negative if and only if it makes a non-negative inner product with all non-negative vectors. So you have to parse all that, but when you do, you'll realize it's actually correct. Okay? Another one is the cone of positive semi-definite matrices. Now there, I have to say what the inner product is. And the inner product is this: if x and y are symmetric matrices. There's lots of ways to say it, but one is trace xy, and that is absolutely nothing but the following, right? It's this sum. It's basically vec of x transpose vec of y, right? Where I simply write out the matrices as vectors. Okay, so that's the inner product, the standard inner product on symmetric matrices, and this says, now this is less obvious. This is self-dual. It says that a matrix is positive semi-definite if and only if its trace against all positive semi-definite matrices is non-negative. So that's what this is saying. It's a non-trivial statement. It's not hard to show. I mean, if you know a little bit about linear algebra, you can show this. So it's not hard to show, but it's actually saying something. So what I'm saying is that little formulas like that pack a lot of meaning into a very small number of ASCII characters. Okay, as you know, as usual. Okay, a couple others, things like norm cones. Here is the Lorentz cone, or the cone associated with the Euclidean norm, and that cone is also its own dual, right? So that's the same thing. And here's the L1 norm cone, and that the dual of that is in fact the norm cone associated with the infinity norm. Okay, and again, that's something you should not be surprised about. I mean, you should expect these things. Okay. Now, if you have a dual cone, if you have a dual cone of a proper cone, that's going to be proper as well, and then it defines an inequality. So you can talk now about a vector being non-negative in the dual inequality. And what it means is this. This is just basically, this is shorthand. It says the following. To be non-negative in the dual inequality simply says you make an inner product which is non-negative for any vector in the cone. So it's basically just a macro for saying that. Okay, so that's the again, none of this has any context right now, but it will. Well, there's a connection between minimal elements. Remember, these are the two extreme ideas of minimizing something with a vector inequality. And one is this: if you have a minimum element, that's characterized the following. If you have a minimum element, it's characterized this way. If you take any dual positive vector, if you minimize lambda transpose z over the set, you always get the minimum element. Remember, minimum elements are unique. That's one way, and we'll come back to this later. It will tell you that you can get a minimum element. Well, if you're solving optimization problems, you just minimize any non-negative linear combination of the elements of z, and that will give you a minimum, the minimum element. Minimal element goes something like this. If you minimize the inner product lambda transpose z, where lambda is dual positive, then you're guaranteed the result is minimal. And so the picture would be something like this. Let's take r plus 2, right? So that's this cone. And of course, what that means is that to be less than or equal to a point or something like that is everything down and to the left. That's what it means to be less than or equal to in this cone. Now, minimal is basically this edge here. These are all minimal, because if I take any of those points and I put something like this here, it only intersects S at that point. So those are all minimal points. This one portion of the boundary are the minimal points for this set S. And what this says is, take any lambda that's positive. The dual cone of r plus 2 is r plus 2. So it says take any two positive numbers, lambda 1, lambda 2. So you take a lambda that points, somewhere like that, and it says minimize lambda transpose z. That means basically to go as far as you can, if that's lambda, in this direction. And you'll find basically a point of contact here, which is minimal, right? So that's the picture. Okay, so and that's for a convex set. And again, we'll come back to all of this later. This is just your first glimpse at this, and no more. Okay, so let's just quickly look at an application of this. And if you've taken economics, you've maybe seen this. So here's the idea: is I have something I want to build or do or produce. And that takes different resources. And here I've drawn it in two variables. That's kind of silly. It's with like fuel and labor, right? So I can use more fuel or I can use more labor. And then every point here, this is called the production set P, gives you a possible method for producing that product, right? So, and in fact, there could be, so theoretically, I mean, in principle, every single shaded point here actually should be tagged, or along with it should be a method for a full description for how you should make that product. And in fact, this is how much fuel that method uses, and this is how much labor that uses. Okay, so that's the idea of the production set. Now the idea is, and then we do this in Rn, where you'd have n resources. And here we're going to use the assumption all of these resources are valuable. In other words, all of them, you don't want to waste any of them or anything like that. Okay, so in that case, it turns out minimal has the obvious meaning. A minimal point in the production set is exactly, and that's with respect to r plus to the n. A minimal point is one where it doesn't intersect this thing, and that's good. It means that there's no other method for producing that product that uses, or if there is another method that uses no more of each resource, then you're back to that method, right? So that's what it means. Or another way to say it is, if someone says, I'm going to operate my factory here, there would be other, I mean, the technical term is non-minimal, and another technical term for this would be stupid, right? Would be the other one, because, I mean, basically, look, all of these points here are methods for doing exactly the same thing with less. I mean, for example, this point here does exactly the same thing. It uses the same amount of fuel, but less labor, right? And under the assumption that all of these are valuable, that's worse. Okay, so that's the picture. Now, our prescription here tells us that a way to find a minimal point is to take something that's dual positive and minimize that linear function over the set. So what it says is you should minimize lambda transpose x. Here, lambda is a set of positive numbers, and in fact, they have a perfect interpretation. These are prices, right? So lambda 1 is the price of resource 1, lambda 2 is the price of resource 2, and it says set any prices you like. Find the cheapest production method, right? So you find the cheapest production method for those prices, and what's guaranteed is that production point is minimal, or I guess they call it efficient. Pareto optimal is another name for it. We're going to come back to all of these, by the way, later in the course. So this is just a glimpse at these ideas.